Good afternoon, everyone. Welcome to our fourth press conference today and last one. This is going to be on the countdown to Cassini's grand finale, and it's a press conference organized in collaboration with the European Space Agency. And taking part in this press conference, we'll have Nicola Zaltobelli, who is the ESA Cassini project scientist. Then we'll have Athena Costenis, who is a Cassini co-investigator at the Laboratoire d'Etudes Spatiales et d'Instrumentation in Astrophysique at the Observatoire de Paris-Médot in France. Then we'll have Hunter White, who is the Cassini plasma spectrometer and ion and neutral mass spectrometer PI, and he's based at the Southwest Research Institute in San Antonio in Texas in the US. And finally, we'll have Luciano Yes, who is a Cassini team member based at University of La Sapienza in Italy. And I'll hand over to Nico. Thank you.
Hello, good afternoon. So we are here actually today to celebrate kind of the beginning of the end of a journey of a fantastic mission, the Cassini-Huygens mission, which is a collaboration, international collaboration of NASA, ESA, the European Space Agency, and ASI, the Italian Space Agency. As you may know, last Saturday, the final Titan flyby of the mission was achieved, putting the trajectory of the spacecraft on its final trajectory. We will have now 22 final orbits until September, until the 15th of September, where Cassini will plunge into Saturn atmosphere. And what we will show you today is here a sketch of the final seconds and hours of Cassini. We will have a presentation by Athena, by Hunter, and by Luciano on different fundamental aspects of the mission. Let me give you briefly a retrospective on what Cassini has been doing so far. So this is here a sketch showing the mission. You see that we have been operating for 20 years, including the cruise phase, and then we had this different mission phase of the mission, the prime mission, equinox mission, the solstice, and now we are here after the end of the proximal orbit of the F-ring grazing orbits, and now starting the final phase of the equinox mission, of the solstice mission, which is the proximal orbits. Cassini has brought up a wealth of discoveries. Actually, we will have to rewrite many textbooks on planetary science in different topics, very broad topics. So we have Titan, its climate, its geology, the rings, their complexity, their complex dynamic. We have the atmosphere of Saturn, the storms. We have the complex processes of the magnetosphere, and of course, last but not least, the icy moons, where we have uncovered completely new worlds. You will hear a bit more about that in the next minutes. So I will hand over now to Athena.
Thank you, Nico. Right, so pleasure to be here today. As Nico said, it's been 20 years we've been working on this mission, and I was a young student at the time when we started programming and developing this mission. I had just finished my PhD thesis on Titan, and nobody was interested in Titan at that time, which may seem strange today, but it has followed me throughout my career, as you can see, because I'm still working on Titan today. I'm a co-investigator on the composite infrared spectrometer on Cassini, and I was a co-investigator on two of the instruments on the Huygens probe that did also fabulous work. But many of us, more than a few thousand people, have been working on the Cassini mission in the past 20 years, as you've heard. And we all of us have found something to be enthusiastic and excited about. My part, my bread and butter is actually Titan, as I mentioned before, but looking at it from the point of view of the habitability and how do we look for habitats in the outer solar system. And essentially, we're looking for requirements such as the liquid water, essential elements, nutrients, and stable environment and energy sources, which is actually what we have on our own planet. And we've moved away from the paradigm of the surface habitats, which is actually what we've always been looking for with liquid water on the surface, for which in our own solar system we basically only find our own planet, think this has gone dead. Yeah. Right there in the middle of what we call the habitable zone, which is actually the area around our sun where the liquid water can exist on the surface, to a new source of excitement, which is the deep habitats. And the deep habitats are actually the moons, the icy moons around the giant planets. We're talking about Jupiter and about Saturn, essentially. And you have here depicted, on the one hand, around Jupiter, Ganymede and Europa that we're looking at, and we're going to be looking at it in the future with dedicated space missions, and around Saturn, Titan and Enceladus that have proved to us that the habitable zone is actually not restricted to surface habitats, that we could have liquid water underneath the surface. And so we're looking in the outer solar system, and of course the Cassini mission is what revealed to us two of these satellites around Saturn, Titan and Enceladus. You'll be hearing more about Enceladus from Hunter in a minute. I just wanted to say that nothing that came out of this mission was really expected or imagined or modeled before. We had many surprises that actually led us to review our models, led us to rethink our whole concept of the outer solar system. These moons are exciting places to look uniquely because there's nothing like Titan anywhere else. There's nothing like Enceladus, but Titan still bears a lot of relevance and a lot of similarities with our own planet. This is the only other place where you have a dense nitrogen atmosphere in the solar system, 95% to the 80% on our own planet. And you also have all the features that you see here on Titan's surface: mountains, dune fields, lakes, volcanoes, all these things that we could never imagine before, including channels that might have had liquid flowing through at some point, and so on. And Enceladus, of course, nobody imagined that this small, tiny moon would have these geysers coming out of the southern polar region. But this was the first clue that we got that you might get liquid water underneath the surface of an object at 10 astronomical units. The habitable zone is supposed to stop at 5 astronomical units. That's where the water is supposed to start freezing. And here you have a moon expelling geysers out in space, 400 kilometers in space, indicating that there's liquid water underneath the surface. So all of this has been revolutionary for us. Nico just told you that we've had 13 years since we arrived in the Saturnian system. We arrived just after the winter solstice in the northern polar region of Titan, and then we're finishing with the summer solstice now. That means basically that we covered just 2 seasons on Titan, because Titan follows Saturn, of course, on its course around the sun, which takes 30 years. So a season is 7.5 years. So in those 13 years, we've only seen 2 seasons on Titan. And Titan's atmosphere, as I just mentioned, is very exciting, not only because of the nitrogen component, which is the major component, but also of the organic chemistry that we have in Titan's atmosphere. Very reminiscent to what we have on our own planet. Wouldn't you like to see the Earth at different seasons? Would it be enough if you just had winter and fall? No, because you would have missed summer and spring. So what we want to do is, of course, to go and explore more extensively Titan's atmosphere. It's very complex. Hunter's instrument here showed us how complicated this chemistry is in the upper part of the atmosphere, with all these complex organics falling through and creating larger and larger molecules that eventually drop on the surface. You can see here a whole host of molecules and organics, hydrocarbons, nitriles, precursors of what led to life on our own planet. So we really want to get to Titan's atmosphere, get a better understanding and the variability, the seasonal effects. But of course, we also want to explore the discovery of the subsurface liquid water ocean on Titan, and Luciano has done a wonderful work there, indicating from gravity measurements. We have spin, also indication that there is a very strong presence for the liquid water ocean sandwiched between 2 ice layers in this case. The water would not be in direct contact with silicons. It would not be expelling anything out to space, but we have a liquid water ocean somewhere beneath Titan's surface, and this is very important, again, for habitability questions. Enceladus plumes, so Hunter is going to say more about the most recent discoveries, but again, as I said before, what is the origin of these plumes is still unknown. How we create them, how we manage to get all this organic chemistry in the ejecta from the plumes. Remember, I mentioned the habitability criteria, and I said liquid water, organics, energy sources. All of these things seem to be there, present on Enceladus. And you'll hear more about what we see in the plumes in a minute. So both of these objects, Titan and Enceladus, are actually places from where we learn a lot of things about climate evolution, organic chemistry, seasonal changes. The composition that we have in there, the sources of heating on icy worlds, is important because not only teaches us something about the outer solar system and the formation of our whole solar system, actually, but also it tells us a lot of things about the Earth's current climate, organic chemistry, possibly about the emergence of life, but not only now, today, in the past and in the future. We get hints from these bodies about the Earth's future status, the Earth's fate, in a sense. So, as Nico said, we're going to have to say goodbye to this amazing mission at some point. Here is the grand finale timeline. We've been thinking about it since November 2016. I have another 5 months to get very emotional about it until September 2017. In the meantime, we're going to have the opportunity to top off this wonderful mission with a lot of new measurements for the rings, for the Saturn's interior. When we get into Saturn, we'll get the composition, the dynamics, the structure of the atmosphere. We're expecting the first dive through the gap that Nikon mentioned before tomorrow. And after that, we're going to be looking at amazing high-resolution data from the rings and everything else. So looking forward to topping off this fantastic mission with more fantastic observations and results. And just to say that I worked on the Voyager mission 10 years after the mission itself. So you can see at the time of the Voyager that had taken, 300 spectra of Titan, and we worked on it decades later on. You can imagine how long we're going to be working on the Cassini mission in the future. Thank you.
Okay, so I would like to tell you a little bit more about Enceladus. I want to concentrate on what we recently did on an October 28, 2015 flyby, but let me briefly just kind of recap a little bit more of the history of discovery. It was, I don't remember the exact year, probably 2005.
Mm-hmm. 7. No.
I said 2006 this morning, but maybe wrong.
All right.
Yeah.
So it's been a long time, but back at one point where we flew by fairly far away, and the magnetometer says there's a strange deflection, in the magnetic field, and you should retarget. And the next flyby and look, and we did, and we saw plumes. Now these plumes, what you can see in this picture, you can see the plumes, and what we see in visible light really is just scattered light off of ice grains. And that makes up a small percentage, maybe 2.5% of the mass. The rest of it's in gas that we don't see. So there's something like 205 kilograms per second of material coming out of it. Maybe 5 of it is grains and 200 of it is gas. And our instrument looks at the gas component, and it uses, there's a picture of the instrument here. We had normally used the closed source. In the closed source, the gas comes in and it thermalizes in this bulbous chamber that's in the top of the figure and is analyzed. But that led to some difficulties in our search for H2 and molecular hydrogen in particular. And so we operate in the final flyby where we were doing in situ measurements. We operated in an open source mode, which is the ambient neutral gas flowing in the lower aperture, And that allows a minimum of interaction between the gas and the instrument before we actually measure the composition. That led us to be able to determine that there was indeed molecular hydrogen coming from the plume. Let's see if can I advance this? Or, okay, there we go. So this was the measurements we made. So we interleave what I called the closed source. The closed source we'd used before because it was 400 times more sensitive. And so that's why we were reluctant to change the open source, but it was the only way to avoid the things that were happening inside the instrument that were confounding our understanding of H2. So you can see the closed source data on the top figure for mass 2 is the hydrogen, mass 18 is water, and mass 44 is carbon dioxide. And in the lower panel, you see a fairly structured water signature going up and down because of the different look directions we were pointing the instrument in, electrostatically, that is. And then and also in the lower panel, you see the greenish material, and that was the hydrogen that we were actually targeting and looking for. There's two things that we were able to basically imply, or the implications of these measurements. One was that the major source of the hydrogen comes from hydrothermal systems in the interior. This had already been indicated about a year ago by the CDA data that indicated silicon dioxide, but this was a further reinforcement that hydrothermal processes were happening in the interior, and there was water actually reacting with the rock that contained iron and taking the water and actually taking the oxygen away to form another mineral and produce H2 as a byproduct. So this was a very important, and the importance comes from looking at this figure, and I know it's a bit complicated, but I have to apologize. The importance, it comes in trying to analyze the H2 or the molecular hydrogen in the context of the other gases, in particular CO2 and CH4. So this reaction that's shown at the bottom indicates a process that we know in the Earth's ocean is methanogenesis, where microbes take H2 and CO2 and form CH4. And that's the way we know, and this process in a cold ocean would take more than the lifetime of Enceladus to occur. So it's biologically enabled. Now, we're not making any claims of life in this, and I'll come back to that. But what we were able to show is that the hydrogen that's available, put in the context of these other constituents, there's chemical energy present. So there's food for microbes in this ocean. And that's the energy source that Athena was referring to earlier. So as she said, we got water, we got organics, we got an energy source. Then there's elemental composition CHONPS, so carbon, hydrogen, oxygen, nitrogen, phosphor, and sulfur. And we've seen all of those with the exception of phosphor and sulfur, and we think that's just because they're in smaller abundances than we've been able to detect before. So it'll take a future mission, but those are all of the checks on the box for habitability. This place is, by all accounts, a habitable ocean in the interior of Enceladus, and that's quite exciting. So this is the summary that I would like to just go through. We did observe the H2. It does imply a hydrothermal source of interaction, and this, in the figure, you can kind of see, I can't get, that thing won't work. You can see that there's water flowing up under the rock, see the reddish portion near the bottom of that figure? That's the water flowing through hot rock that has been heated by tidal processes and forms hot spots, and these are supposed to be indicative of plumes. They're like, we are modeling them after white smokers on the Earth, but we don't know exactly how this hydrothermal system looks. It's just an idea, but it does expel material into the ocean at a high temperature that actually then comes into equilibrium with the ocean and ends up in the plume and then exits. And we're able to measure the composition of the ocean by just looking at the plume gases itself. And like I say, this is not an indication of life. I use the term agnostic with regard to life, because you can make arguments that the hydrogen affinity we measured is too great for life to exist, but I can make equally as good of arguments, and maybe more, that there's no reason to suspect that we even know what the affinity should be in this situation, and that we should keep our minds open. Clearly, we should return. The answer, whether there's life, we all know that would be a very exciting result. But even if there isn't life, we need to know that too, because we need to revise our checklist if we haven't gotten it right. So I'll stop there and pass it to Luciano.
Thank you. So it's really incredible how much we know about this tiny moon, something that was completely unexpected before Cassini got there. And however, it's impressive how many questions Cassini raised. And all these questions are fundamental, very interesting. So a lot of work for the future generation of scientists. So I would talk about the final part of Cassini's life. And really it will be fireworks, because by going through the rings, Cassini, between Saturn and the rings, Cassini will carry out measurements which would otherwise be impossible. So Cassini will be skimming Saturn at an altitude of 3,000 kilometers, so a lot less than the radius of the planet. The final Titan encounter was 3 days ago. And let me recall that Titan was the real engine of the mission. It was not only one of the main scientific objects of scientific interest of the mission, but it was the true propulsion system of the mission. Because by targeting Titan in a clever way, Cassini was able to visit all the moons of the Saturnian system many, many times. If we would have failed a Titan flyby, then the mission would have been essentially over, or almost over. So this final flyby put Cassini into the very eccentric orbit that you see there in blue. We will cross the ring plane, a dangerous moment for the mission. We think that everything will be okay, but there is some risk, of course, because there are rocks, tiny particles, etc., at a speed of about 30 kilometers per second, so pretty fast. And after this first ring crossing, which will take place tomorrow, Cassini will do 22 orbits of essentially the same type, same eccentricity. And by going closer to Saturn, there are essentially two instruments that will be able to provide information about the interior structure of the planet. Remember that we have only ideas so far on how Saturn is made in its interior. And magnetic field and gravity measurements are the only tool that are able to go deep below the cloud level. These are long-range forces, and therefore they tell us about the deep interior structure of the planet. In the sketch that you see there, you see essentially what we hope to get with these 22 final orbits. We would like to determine how much hydrogen and helium are in the outer parts, in the envelope. And we will be able to measure it by means of the gravity field. It's not the gravity field of a sphere. Saturn is oblate, and we will measure the details of the gravity field. We know the density, the overall density of Saturn, because we know the mass and the volume. So what is missing cannot be but concentrated in the core. And the core is made up of silicates, heavy elements. For astrophysicists, heavy elements is everything that is not hydrogen or helium. So we hope to get a measurement of the core mass, how many heavy elements are concentrated in the interior of Saturn. So, and this is, of course, very important to understand the formation processes of the Saturnian system. Another important measurement that can be done, this only from gravity. The previous measurements will be made thanks to gravity and magnetic fields, is the depth of the winds. We know that Saturn is a place where strong winds, you can see the banded structure on images of Saturn. The same happens for Jupiter. These are indicates the zonal winds. And however, we don't know how deep these winds, which range from, let us say, 100 to 300 kilometers per hour, how deep this wind go, what is the depth of the wind. And we will be able to determine this depth, can be 300 kilometers, can be 1,000, can be 3,000, or even go down to the deep interior. We will be able to know how deep they go. For gravity, it's nice to see that the two agencies, together with the Italian Space Agency, which provided instrumentation on board Cassini, the two agencies, NASA and ESA, started this mission together and will conclude this mission also together, because Cassini will be tracked both from the ground antennas of the Deep Space Network and from the ESA antennas in the southern hemisphere, in Malargüe, Argentina, and New North, Australia. Cassini has a much better visibility in this period from the southern hemisphere. So the two antennas of the European Space Agency are very well placed in terms of geometry. And both antennas, NASA and ESA, will be able to provide very accurate velocity measurements of the spacecraft. Let us say 0.02 millimeters per second. This is about 20 microns per second. We can do a lot better at longer integration times, but it's remarkable that these velocity measurements can be carried out with such an accuracy over distances which are more than 1 billion kilometers. This is, I teach aerospace engineering, I teach this to my students, but when I go to these places, to the tracking stations, it's really amazing to think that we are able to measure with such an accuracy so distant objects. And these measurements, of course, will be provide the observable from which we will determine the deep interior of Saturn. So, finger crossed, tomorrow we will know whether we survived the ring crossing plane. I'm optimistic, but you know, there is always a risk.
Okay, I would like to say a few words again, taking a broader view on Cassini. So, in fact, we have to see Cassini as a step toward the discovery of a new type of habitat. You have heard that the icy moons actually bear surprises in terms of habitability. And what Cassini has done is really expanding our view on what worlds might be habitable. And far from the sun, this applies also to exoplanets. Far from the host star, you can be well beyond the line where the liquid water is stable on the surface of the body, but still have condition where water can be kept liquid below the icy crust of an icy moon. So if we look at this sketch from the discovery of the icy moon for the first time by Galileo, then the first glimpse, the first view of them by the Voyager spacecraft in the 70s, then we had actually on Earth research going on the deep ocean habitat that Hunter has mentioned. Then we went back to start exploring with Galileo, and Cassini has proven that all these theories with data are actually supported. And this might be, the icy moon might be one of the most common habitats in the galaxy. In the meantime, you had all this discovery of exoplanets, and for this you need gas giants. You don't need the the search for small moons, Earth-like, small, and so on. You need all these giants that have been already discovered. Many have been discovered, and then you just need icy moons around with a little bit of eccentricity to maintain the energy necessary to keep the water liquid. So the next step are really taking Jupiter as an archetype of a gas giant is the mission JUICE by also an international collaboration between ESA and NASA, and possibly future landing in the future. So there are actually two missions now being prepared at nearly the same stage. So this is a ESA, the main partner is ESA and Europa Clipper by NASA, that will be dedicated this time to study the habitability of those ocean worlds. So you can see on the bottom of the page here the JUICE mission and the Clipper mission here, and you see that both missions will face the challenge to have very large solar panels in order to gain their energy so far from the sun. And actually, I like to talk about JUICE as the first ever orbiter of an icy moon. So the Europa Clipper will perform multiple flyby of Europa, characterizing this moon in depth, and JUICE will be able here, this is a simulation here at 500 kilometer altitude above Ganymede. We will have the first orbiter. JUICE is the first large-class mission of the Cosmic Vision program of ESA. We will not only study Ganymede from the orbit, but also investigate Europa and Callisto using flybys, Cassini style. And the last mission phase, as I said, will be then this orbit around Ganymede. So this is the final slide, summarizing the JUICE science goals here. And this is really the heritage of Cassini. You have heard about habitability being the result of three key ingredients. You need liquid water for life as we know it, of course. Yeah? So we need liquid water, we need a source of energy, and we need a source of nutrients given by some chemical equilibrium there. So, for example, the H2 that have been detected on Enceladus that may be reminiscent of these smokers, black or white, on the deep ocean floor. And what JUICE will do is then study those moons in detail, the surface, the geophysics, their interior structure, and also very important to understand their interaction with their environment in order to study any transport of material from the inside to the outside. Because Cassini has shown this is really what matters to understand the interior of those moons. And this is it. I think we will take a question from there.
Thank you very much for your talks. We can now open the floor for questions. Are there any questions here in the room?
Hi, it's Jonathan Amos from the BBC. I've got a few, actually. Could you, all of you, speak to one of the other thorny issues which we hope to resolve in the next few months, which is the mass of the rings, the age of the rings, and the significance of understanding that?
So, yes, indeed. I didn't mention the mass of the rings. While, you see, in the past, we were not able to determine the mass of the ring because Cassini was flying outside from the rings. So, essentially, the contribution from the rings to the gravity field mixed up with the oblateness of Saturn. It was impossible. But by flying between the rings and Saturn, you can, Cassini will be able to disentangle the two effects. So the mass of the rings will be measured with an accuracy which is about 10% of a MIMAS mass. And this will be important for people doing interpretation to assess how old the rings are. And barely speaking, if the rings are massive, this means that they are old. They can date back to the formation of the Saturnian system. If the mass is small, then the rings are young, and they have been formed by a different process. So something very interesting. We will be doing the measurements. There was a talk this afternoon by a graduate student of mine. And I know that in the project, people, my colleagues, are betting on the ring mass. We don't know. We are not allowed to bet, but we will provide the mass of the ring with fairly good accuracy, and so we will be able to resolve this controversy.
So if you think you'll get within 10% of the number, what are we...
MIMAS mass is a small satellite, small moon of Saturn.
Oh, MIMAS. Okay, right, yeah. What's the error currently? I mean,
Oh no,
yeah.
we don't really know.
I mean, we out by. I mean, how far out?
The GM could be 2 in terms of, I know, in terms of several MIMAS masses. Right. Several MIMAS masses is the current uncertainty. Because the problem is that the B ring, which is the most massive one, is also optically thick. So sunlight is blocked, and you cannot assess well how much mass is. Essentially, is a curtain. You cannot see through. While the other rings are somehow transparent, and so from the attenuation you can understand what is the surface mass density. So the B ring, since it blocks, you don't know how thick it is. It blocks, just blocks.
So we will also measure
waves.
The ring composition, because indeed the B ring contains most of the mass, and with the standard method of occultation, radio occultation or UV occultation, you cannot really peer through it. But the interesting fact about the ring is that it's made of nearly pure water ice. And this is weird. If it's a very old object that was formed at the same time as Saturn, how come that it looks so fresh, although it's actually exposed to interplanetary meteorite bombardment and so on? So there are really two competing scenarios. A scenario where the ring can be old, where you would get only ice by having a moon of the size of Titan already differentiated, migrating towards Saturn as there was some gas still left, and then being disrupted by tidal forces, and then you would lose the silicate fraction into Saturn, and you will get the ice in orbit. So that's one scenario where the ring could be old. The other scenario is that you could have gotten a comet-type object tidally disrupted, but in this case, why are the rings so pure and missing so much silicates? We know since Rosetta that actually your comet is more sand, which is icy, rather than a dirty snowball. So we are missing really the detailed composition also of the rings. And this is something that during the proximal orbit, during the F-ring orbit, we could collect with the Cassini cosmic dust analyzer some of the grains ejected from the rings, kind of a dusty atmosphere above the ring that will tell us about more in detail about their composition. And with a mass given by radio science, that should settle the score.
So it's just one number, the mass.
Yeah, the mass.
That's it. So it doesn't lie. That doesn't lie. Then can be controversial about the interpretation, but...
Okay, and another question, yeah. Sort of kind of looking to the future. Hunter, where is... so we've got the New Frontiers competition, haven't we,
Yes.
with NASA, and I guess your community has submitted for that, yes?
That's correct.
Right.
Yeah, well, in a couple of days they will.
Yeah.
Yes.
Have you coalesced around one idea, one proposition? What
I think there are at least 2 competing propositions about going back to Enceladus, and I think there are probably 2 proposals for Titan as well. So I think there will be at least 4 proposals going back to the targeted going back to the Saturn system. There might be a fifth that is a Saturn probe into the interior as well. So there's a fair number of proposals that are targeted for the Saturn system in the New Frontiers program.
Right,
Between
and-
that and the M5s of ESA.
Yeah, well, I wanted to get on to the M5s. I mean, there's been a view in the planetary community that because they haven't had an M5 or haven't had an M mission yet in Europe, and there is, I guess there's this view that Europe can't do a planetary mission for the M cost cap.
To the Saturnian system? you mean?
Well, I mean, you tell me. I mean, Marco Polo was too expensive, and that wasn't going out anywhere near as far. So, I mean, can Europe do anything, contribute anything here, if it's not an L class? Can it do something in the M class, even if it's to ride with NASA again, as they did with Huygens?
So I have been submitting some of those proposals, and indeed we started out with very large missions at some point because it seemed desirable to go out to the outer solar system again with a very complete mission, like Cassini. Since then, we've got the L1, which is to Jupiter, JUICE, but there have been several proposals, as you say, to the M4 and to the M5s with very reasonable cost scenarios to return to the Saturnian system. I don't think the problem is the cost or how to get there, because we have ways to do it with now scenarios that do not include a full mission, but there is a lander or there is a dedicated orbiter or there is something. As you say, I think today we need to do the collaborative effort has to be more efficient. And in troubled times, as I would call them, where we don't know exactly where we're going with space exploration from the space agency in the United States, and also ESA, don't forget, has gotten its ministerial recently where the budget was not exactly up to the level where we would have expected for the mandatory science program. I think the agency has to strive to find ideas about how to go out there. The proposals are on the table. The discussions are actually happening with the other side. We did not get a planetary mission in M4, and I agree with you that there were proposals there, but they've come up back in M5. The Saturn probe we see on both sides of the Atlantic. We see proposals for returning Titan and the moons on both sides of the Atlantic. And those have not been dismissed yet, either for the M5 or the New Frontiers, of course, that haven't been submitted yet. So the hope is to find a way to do a mission there.
If planetary doesn't get M5, it's the 2030s before it'll, whatever it is, if we were to get M6, it won't go until after JUICE.
And don't forget that there's also the icy giants, there is also currently a study happening for that part, which was also one of the major science themes that came in from the L discussions for a large mission. But there have been proposals submitted within the M for going to Uranus. And so I don't think we cannot do it. I think, it's a matter of programmatic decisions and things like that.
But if I may add something, the current structure of enhancement of opportunity, etc., is not really favorable to collaborative efforts. It may work for very large missions, for example, something Clipper Europe could contribute, but every proposal has to go through an enhancement of opportunity and pass an enhancement of opportunity. So suppose, for example, just to make an example, Clipper. Suppose that there is room for a European element on the Clipper mission. Of course, you have to go through an enhancement of opportunity, had to come in the right time, because NASA cannot wait for all the not smooth processes of the selection, identification of contractors, etc., that we have in Europe. So, if I can be a little bit polemic, the current structure of the European Space Agency is not really favorable to, does not make easy collaborative efforts. I don't know whether you agree or not, but
Well, the NASA is not particularly much better in that regard either.
it's not better. Okay, so we are mixing two difficulties on both sides of the Atlantic. So I'm wondering whether something like Cassini can take place in the future. I'm not optimistic.
Thank you very much. Are there any additional questions from here in the room? If not, I think there are a couple on the web stream.
So this first question is from SciTechno blog, and the question is for any of the members. It is, how long will Cassini transmit data before burning in the planet's atmosphere?
Your data.
Well, they will be, one of our goals is to try to get atmospheric data as low in altitude as we can. And our ion neutral mass spectrometer measurements will be one of the primary measurements that is being made during that period of time. We will hit a point where the dynamic pressure is high enough. We will have the orientation of the spacecraft with the antenna pointed back at the Earth, and at some point the boom, the magnetometer boom, which is a big surface area, a long lever arm, will torque it so far that it loses lock on Earth, and that will be the end of the data. And that will be before the spacecraft is destroyed, but the dynamic pressure will eventually catch up with the boom.
Are there any other questions? There are still some in the web stream, so I think we'll just ask another one there. But the priority is for the journalists here in the room, if anyone wants to ask any additional questions. No?
Okay. This question is from Cesar Guaita. I hope I'm pronouncing that correctly, from Milano Planetarium. And the question is, what is the maximum resolution available for the ring system during the grand finale? And what about the possibility to resolve propellers?
350 meters per pixel. But no, the propeller have been resolved actually during the F-ring orbit. So the one you see on the screen, the one in white. So in the airing, we had actually wonderful views of those propellers. The body itself, which is at the origin of the structure, can still not be resolved, but you can very well see the propeller structure in detail.
Thank you very much. If there are no more questions here, I think we'll finish. Thank you very much to our speakers for the brilliant talks. Thank you all for coming. The next press conference is tomorrow at 10 a.m. and it's on finding traces of human presence in caves and soils and landscapes. Do come along. Thank you.